Okay, so let's start. Okay, so uh, last lecture we were looking at a MOS capacitor, and I mentioned that in a MOS capacitor, the inversion charge comes through thermal generation, and it's a slow process, and it can take seconds or even minutes for the inversion charge to form. But if we place an N plus layer here next to the interface here, then what happens is the inversion charge or the electrons can easily come from the N type, and then the inversion charge can form very rapidly. So and you recognize that this is a part of a MOSFET. If I put another N plus here, then it basically becomes a MOSFET here. So what we are doing is progressing from a MOS capacitor that you see here towards a MOSFET. And so we have a 3-terminal structure that you see here. Okay. And the issue is, when I look at this structure, we've already calculated what is the condition for threshold. We have obtained an expression. And the question that we want to ask is, what is the condition for strong inversion here? Or what is threshold voltage here? Is it the same as this one? Or is it different? Okay, so that's the question that we are asking. And in order to illustrate this, the difference between the two structures, let me pose a couple of questions, the answers to which we will look at subsequently here. All right, so back to MOS capacitor. So we have here threshold voltage. If I calculate for the numbers that I've given you, 100 nanometers of SiO2, doping of 10 power 16, the threshold voltage turns out to be 1.4. All right, it turns out to be 1.4. So if I apply 1.4 here, obviously I would create a inversion layer here. It's just the beginning of the inversion layer here. The electron density, at the surface at that particular point of time is equal to Na, whatever is the doping here. That's the condition for threshold. So obviously, when I'm saying Vt is equal to 1.4 and I apply 1.4 here and 0 here, obviously I'm at the threshold, right? So I will create an inversion layer here. What about this situation? Suppose I make the top ground and I apply minus 1.4. Will I have an inversion layer here? Am I at the threshold? What do you think? I apply 1.4 here and 0 here, or ground here and minus 1.4 here. Any difference? Any difference between the two? No, why should you have doubts? It's a 2-terminal structure. What matters is the effective voltage between the two, right? The effective voltage is 1.4 here from gate to body, and the effective voltage is also 1.4 from gate to body. So I will have a inversion charge here and all that. So it's the same. All right, that's clear. So again, as I said, 1.4 ground will create Ns equal to Na here. Let's look at this structure here. Well, I put here 0. I put here 0. And I apply 1.4. Will I create an inversion layer here? Yes or no? Yes? Everybody agrees? I will create? Okay. Well, how do I get 1.4? What we did was we solved the Poisson's equation along this direction, right? Starting from the gate to the body. And we found out how much band bending is there. And from there, we figured out that the surface potential was 2 phi f. And we arrived at this number 1.4. Exactly same structure, same gate, same SiO2 thickness, same doping in the p-type. Nothing is changing. And I'm asking, if I apply 1.4 here, knowing that the body here and the source here is at 0, will I get a threshold voltage? Am I at threshold voltage? The answer is, all of you are saying yes. Okay, fine. Remember, Vt is the voltage at which the surface electron density is equal to the background doping. That's our definition of Vt. Okay, all right. What about here? If you all said, when I go from 1.4 to 0 and I achieve threshold, all right, then let me ask this question here. This is still 0. This is still 1.4. But this I've made it 1 volt. Will I have threshold? I go from here to here is the same as I go from here to here. Will I have threshold or not? Yes or no? $1.40. 1.4, 0. Same structure, everything same. Will I have threshold? Is my device at the onset of inversion? All right. This is even more interesting. The next one. Look at this one. We said whether you apply 1.4 here or 0 here is the same thing, right? And so if I apply 0 here and minus 1.4, I have threshold voltage. Fine. I've done and all of you said that if I apply 1.4 here and this is 0 and this is 0, I have threshold. Right now I have this is 0, and this is minus 1.4. Will threshold occur? Will it occur or not? All right. 0 minus 1.4, 0 minus 1.4. Will it occur? All right. So these are the questions. Keep that in mind. There is a distinction. The reason why I'm raising these problems are there is a distinction between this structure and this structure, and we have to understand where that distinction is. Okay, and this is often not talked about in any great detail, and it's a major source of confusion, which remains, for some people it remains through a lifetime, right? So they don't understand the differences between this structure, which is a part of a MOSFET, and this structure here. All right, so let's look at the differences here. Okay, let's understand what threshold voltage is. The threshold voltage is, for us, you can define, threshold is a boundary between strong inversion and subthreshold. So you can define it in many ways. For us, threshold is a point where the surface electron density is equal to, the electron density at the surface is equal to whatever doping is there in the bulk. That's our definition of threshold. Okay, so that's the starting point. So when I ask the question, has threshold occurred here or here, I have to find out, is my electron density equal to Na or not? Okay, so that's what I have to get. Okay, so Ns is equal to Na. All right, so we'll go through this here. So N, we have said, is equal to Ni exponent EFN Fermi level. Now, when I apply a voltage, I don't have, strictly speaking, a Fermi energy, but I can talk about a quasi-Fermi level. So EFN minus EI by KT, right? So that's an expression that we have seen earlier, N equal to Ni here. Now, the reason why I'm writing this expression is because I'm looking for this condition, Ns here. Ns has to be equal to Na. Na is known. Okay. So I have to write here Ns here, Ns equal to Ni, EFN. Now I write EFN S. S denotes surface. So Fermi, quasi-Fermi level at the surface minus intrinsic level at the surface by KT. That's the condition. Okay. Ns is equal to this much here. All right. Now I rearrange these terms here. EFN S that you see here, quasi-Fermi level at the surface. Now I define quasi-Fermi level in the bulk minus and plus quasi-Fermi level in the bulk. So I add these two terms here. In addition, I subtract intrinsic level in the bulk and add intrinsic level in the bulk. Okay, we write it in this form. This one now can be written then is Ni. The different exponential terms are written out separately. Exponent EFN B minus EIB by KT. EFN S minus EFN B, the difference of the quasi-Fermi level at the surface and the bulk by KT, and EIB minus EIS by KT. All right, so that's fine. This one, note what does this denote? Go back and look at this expression here, and look at this one here. What does this denote? Electron density in the bulk. And how much is it? Ni square over Na. So that's fine. I write this out at Ni square over Na. So this is okay. What about this term here? This is nothing but definition of potential. Potential, we said, we are defining as the intrinsic level at any point minus the intrinsic level in the bulk. Bulk we take as reference. Okay. So by definition, this is potential at the surface. EIS potential is minus EIS minus EIB by Q here. So that's the definition here. So with these definitions, I obtain Ns equal to Ni square over Na, exponent EFN, quasi-Fermi level at the surface, minus quasi-Fermi level at the bulk by KT, multiplied by exponent Q. Now note that I'm writing it as psi SB. Why? Because we have taken bulk as a reference. So explicitly I'm writing now, this is surface potential measured with respect to the bulk. Bulk is taken as a reference. Okay, these distinctions are very important. Many times we forget about it. So this is psi SB, surface potential measured with respect to bulk. All right. Now for threshold, we said NS is equal to NA. So we substitute that. Now I write here psi SB, surface potential measured with respect to bulk at threshold, TH at threshold. Now we can calculate from here, rearrange, and surface potential at threshold turns out to be 2 kT by Q, ln Na by Ni. This particular term is what is giving rise to Na by Ni, plus quasi-Fermi level at the surface minus quasi-Fermi level at the bulk divided by Q. This is what we have been calling as 2 phi f. So psi s measured with respect to bulk at threshold is 2 phi f plus EFNS, Fermi level at the surface, minus Fermi level at the bulk divided by Q. Right? So we have a very general expression for what is the surface potential measured with respect to bulk at threshold. Right? And this is this expression. Now, we said that, when I look at it here, if I look at the Fermi level in the bulk, quasi-Fermi level in the bulk, and I look at quasi-Fermi level in the surface here, there's no difference because there's no current flowing. There's no current here. And remember, Jn is equal to the gradient of quasi-Fermi level here. So then we say quasi-Fermi level at the surface here is the same as quasi-Fermi level in the bulk here. So this term drops out and we get the condition at threshold that the surface potential at threshold is equal to 2 phi f. Okay, so we arrive at this one. And this is a general expression that we had obtained, how gate voltage is related to surface potential. So if I now take 2 phi f and put it here, then I get the expression for threshold voltage. All right, so I get an expression for threshold voltage with this surface potential measured from bulk. Right, so I've gone through the derivation and we have arrived at what is the condition for threshold. Okay, so this is the general condition here. 2 phi f plus the Fermi level, electron quasi-Fermi level at the surface minus the electron quasi-Fermi level in the bulk by Q. Right? So now the issue is the following. Here we said quasi-Fermi level at the surface and quasi-Fermi level in the bulk is the same. Now here is an interesting issue and both are the same here. Here, let me show you quasi-Fermi level at the surface, quasi-Fermi level in the bulk, and I have quasi-Fermi level in the source. In the source here, we have three distinct regions now. Surface here, bulk here, and source here. The issue is my quasi-Fermi level at the surface equal to this one or is it equal to this one? What is it equal to? Okay, it may happen that both of them, for example, if I make source 0 and body 0, it means source and body, if I look at it, NP junction, both are equilibrium, and therefore the quasi-Fermi level in the N-type will be exactly same as quasi-Fermi level in the bulk. In that case, both are the same, and therefore my condition would be EFN surface is equal to EFN B or EFN source, and therefore this term will go to 0 and I will have psi s threshold and all. But I can have different situations. Now, what I have been saying to you is, remember we had discussed that when you create threshold, you have an inversion charge here. This inversion charge is what? N-type. And at that point, the channel is connected to the source, which is also N+. Right? And the channel is separated from the body here. So what happens is when you create a threshold condition, the quasi-Fermi level at the surface here, it follows this one here. If there is a competition between, is it going to follow this one or is it going to follow this one? If the two happen to be different, then my quasi-Fermi level at the source will follow at the surface will follow N+ here. N+ here. And so the condition, then this is the distinction that you have to keep in mind, because we create an inversion layer here, no current is flowing in this direction here, and this then, this imposes the what the quasi-Fermi level at the surface is. This is N and N here. While here, note that the bulk is there's a depletion region, and the bulk's ability to create inversion charge is much less than the ability of source layer. Source can easily supply electrons. If you need more electrons here, they can easily come from source. If you need less, the electrons can easily go out. But from the bulk, that connection is not there. If you need more electrons, you have to wait for 2 seconds, which tells you that this exerts a more stronger influence over the channel rather than the bulk here. So the Fermi level at the source, at the surface, will be equal to Fermi level at the source, not Fermi level in the bulk. Okay, so when I write here, what is EFNS? EFNS, quasi-Fermi level at the surface will be equal to quasi-Fermi level associated with the source. So that's the distinction that you have to see here. Here, what is the condition for threshold? Psi SB, you put, anyway, both are equal, so that drops it to 0. While here, this quasi-Fermi level at the surface has to be equal to quasi-Fermi level associated with the source. Okay, so let's see the distinction then. Okay, now if that is true, look at that here. If I write quasi-Fermi level at the source minus quasi-Fermi level in the bulk divided by Q, this is nothing but the difference in the voltage between the 2 points. The difference in the voltage between here and here is nothing but the difference in the quasi-Fermi level at the 2. So what we write is psi SB, surface potential measured with respect to the body at threshold, is equal to 2 phi f plus VSB, whatever is the source to body voltage. That's where we arrive at. So there's a distinction here. We said surface potential is equal to simply 2 phi f. Here we get equal to 2 phi f plus VSB. Now with this you can answer these questions here. As I said, there is an inversion charge here, so it's connected here, strongly connected to this, and therefore it follows this quasi-Fermi level rather than it follows this one. Okay. All right. So in this case, when I apply 1.4, my surface potential at threshold is 0.7. If I apply 1.4 here, note that the condition for inversion is what now? 2 phi f plus VSB. Source to body voltage is 0. And so in this case also I obtain 0.7 here. So my surface potential required is 0.7 and threshold will occur at the same value 1.4. 1.4 here and 1.4 here. The same value. Okay. Why? Because the surface potential required is same 0.7 here and same 0.7 here, which means surface potential is the same, which means charge is the same, the oxide drop is the same, and then the voltage required is also the same in both cases. Okay. Look at the next case here. Again, in this case, it always remains the same. Surface potential at threshold is 0.7. In this case, what is the surface potential at threshold? It will be equal to, if I apply 1.4, if you apply 1.4, what will you end up with? Surface potential equal to 0.7. This is exactly the same electrostatics are there. As you go from here to here, the same you go from here to here. So if you apply 1.4, you will get 0.7. But at threshold, how much do you require? What is the condition that surface potential at threshold should be? 2 phi f plus VSB. So what you are looking for is actually 1.7. And therefore, if you apply 1.4 here, you're not going to get threshold. 1.4 will only give you a surface potential of 0.7, is well below this particular limit of 1.7 here. And therefore, you will hardly have any inversion charge here. In this case, inversion has occurred. In this case, inversion has not occurred. Right? And how much voltage do I have to apply now? Well, I will have to raise this value. If you go from 1.4 to 2 volt, what may happen? This may become 1 volt. Then you apply 2.5, it may become 1.3. Right? So we have this equation which tells us how to calculate. How to calculate a gate to body voltage, here to achieve a particular surface potential. So now we are looking for a surface potential of 1.7. So I go ahead and put 1.7 here and 1.7 here, and threshold voltage now turns out to be 3.2. I have to apply 3.2 volts here to create a surface potential here, which is 1.7, and therefore achieve threshold condition, therefore cause inversion to occur here. Okay, so this 1 volt makes a huge difference. You don't get threshold at the same point as this one. Okay, all right, let's look at this one here. We said 0 and minus 1.4. Again, surface potential, you will get 0.7 with respect to bulk here. What will you get? Surface potential with respect to bulk will also be 0.7, same electrostatics. 0 to minus 1.4. What is the surface potential required at threshold in this case? 2 phi f plus VSB. So the surface potential required at threshold is 2 phi f plus VSB equal to 2.1. I require 2.1 here. I have only 0.7. I will not get threshold. They will be, in fact, is well below this particular limit here. I have no inversion charge. Absolutely no inversion charge here. While here I will have inversion charge. Inversion has started here. While here inversion is not started here. How much voltage do I have to apply? Well, the first thing is, in this case, if you apply a sufficiently large negative voltage, you will create inversion. In this case, you may apply any amount of negative voltage. You will never create inversion. Look at this value here. VGB equal to V flat band plus psi SB. In this case, now I have to apply a gate voltage of 3.85 because note again psi SB has to be 2.1. So I put 2.1 here and then I put this value here, and gate to body voltage has to be 3.85. Gate to body voltage. So gate minus body has to be 3.85. So now you can calculate that I need an additional gate voltage. How much is it? Is 3.85 minus 1.4. So that's the additional gate voltage that you have to apply. Further, you can easily see from here that any amount of negative gate voltage will never create inversion. No, in this case, if you make it 0, you can apply a sufficiently large negative voltage and you create inversion. In this case, you will never create inversion if you apply simply negative voltage. All right, it just follows from here. If you apply a negative voltage here, you will never achieve 2 phi f plus VSB. That condition will never occur. Just look at this condition. All right, what about this case? Will threshold occur? What is the condition for threshold? 2 phi f plus VSB. So VSB is 0. So it will occur. So if I apply minus 1.4, but if I apply minus 1.4 here also, then I can get. But if I had this 0 here, then I will not get. Okay, so these distinctions are important here. So psi SB at threshold is 2 phi f plus VSB. VSB is 0 here, so it's 0.7, and which is fine. If I apply 0 here and minus 1.4 here, I'll get psi s equal to 0.7, just like in this case. And therefore, threshold will occur. Inversion will begin. Okay. So very often you will find students, and even in books sometimes, you find threshold is written as a condition at which surface potential is 2 phi f. Is that a correct statement? What is the correct statement then? First of all, note, when somebody says threshold is a condition at which surface potential is 2 phi f, the first issue that you should raise is surface potential measured with respect to what? Is it with respect to bulk or is it with respect to the source? That issue must arise. Okay, we have seen that surface potential with respect to bulk has to be 2 phi f plus VSB. So a true statement is threshold is a condition at which surface potential with respect to bulk, note I'll underline, with respect to bulk is 2 phi f plus VSB. That's the condition for threshold. But look at this term here. Psi SB is what? Surface potential measured with respect to bulk. VSB is what? Source voltage measured with respect to bulk. Let me write it like this here. Psi S threshold minus psi B equal to 2 phi f plus Vs minus Vb. What is psi B? Potential in the bulk. What is this? Potential in the bulk. These two will cancel. So psi S at threshold minus Vs is equal to 2 phi f. What does this statement tell you? Surface potential with respect to source is 2 phi f. So this statement is not wrong, it is incomplete. Threshold is a condition at which surface potential with respect to source is 2 phi f. Okay, it depends on how you are saying it. If you just say surface potential is 2 phi f, well, it's incomplete. If you say with respect to source, yes, true. Otherwise, you say surface potential is a condition at which surface potential, threshold is a condition at which surface potential with respect to bulk is 2 phi f plus VSB. Okay, so that's, if you're measuring with respect to bulk, then this is the condition. If you're measuring with respect to source, then this is the condition. Okay. All right, so let's start with this. So surface potential with respect to bulk is 2 phi f plus VSB. And we said gate to body voltage. If I start from here and solve the Poisson's equation, I get gate to body voltage is flat band plus psi SB plus square root, this is depletion charge. And if I'm in inversion, then I will have an inversion charge also. All right, so now let's psi SB, let's write it as 2 phi f plus VSB here. So let's write it out. Psi SB as 2 phi f plus VSB here. and psi SBS 2 phi F plus VSB here, minus Q inversion by C oxide. Okay. Now note that VGB minus VSB becomes VGS. Okay. VGB minus VSB is VGS. So I write it here. So VSB has been taken on this side. V flat band plus 2 phi F plus this term here minus Q inversion by C oxide. I can take this, rewrite this as this whole thing is a constant as far as gate voltage is concerned. So I can write this as VGS is equal to VT minus Q inversion by C oxide. And VT I can write now like this here. VT is equal to V flat band plus 2 phi F plus square root 2 ES QNA 2 phi F plus VSB by C oxide. And we obtain an expression for this one here. So Q inversion in a 3-terminal structure like this, capacitive structure, Q inversion is minus C ox, VGS minus VT. VT is given by VFB plus 2 phi F plus this term. Now I can, the rest is rearranging here. I can write this as V flat band plus 2 phi F, square root 2 ES QNA 2 phi F by C oxide. Add this term, subtract this term from here. Rewrite this as VT equal to VT0 plus square root 2 ES QNA here and this term here. This is this part, I've collected it here. This is called zero bias threshold voltage in the sense that when the source to body voltage is 0. And so what you're seeing is the threshold voltage is a function of source to body voltage. How much source to body, and we have seen why. Because the surface potential at which threshold occurs, that depends on the source to body voltage. So threshold voltage is a function of source to body voltage. And therefore, this part is a term which is called zero source to body voltage, threshold voltage. We call it VT0. And this is the part which describes how threshold voltage varies with source to body voltage. So this whole phenomena of threshold voltage varying with body voltage is called the body effect. And so this refers to this one here. And this parameter that you see here is called the body parameter. Okay. Right. So VT equal to VT0 plus gamma square root 2 phi F plus VSB minus square root 2 phi F. Okay. So that's the final model that we obtain here. VT is VT0. All the terms are constants here. And this is the part which depends on VSB here. And that's the total threshold voltage. But things get more interesting here. So far we talked about a source connected here and we have obtained threshold voltage here. But now let's add a drain terminal here. Now this is at Vs and this is at Vd. What is the threshold voltage now? Now we have one more terminal, right? What will be the threshold voltage now? How do I write Q inversion? Well, let's focus our attention here, right at the source end. Now remember, this is our general condition. At threshold, surface potential with respect to bulk should be equal to 2 phi F plus Fermi level at the surface minus Fermi level in the bulk divided by Q. If I apply it here at this point, what is Fermi level at the surface minus Fermi level at the bulk? It will be VSB, right? So that's why we've written at threshold, psi SB threshold should be equal to 2 phi F plus VSB. If we apply this particular equation right here at this point here, next to the source. And then we have written here, right? VGB equal to this expression we have written. And from there we have obtained what is Q inversion equal to. This is a general equation. We have written Q inversion is equal to minus C ox VGS minus, and we were calling this as VT. Right? So that's fine. Now you can see what would I call it here at this point? Suppose I apply. So, and this gives us VGS minus VT. At this point, surface potential at threshold should be 2 phi F plus the voltage at the drain measured with respect to body, VDB. Threshold will occur at a different voltage here because threshold will occur at 2 phi F Fermi level at the surface minus Fermi level in the bulk divided by Q. Fermi level at the surface here is connected to drain here, not to the source. Source is far away. The drain will exert influence here. So this will be V drain to body voltage here. Fermi level at the surface minus Fermi level at the bulk at this point will be drain to body voltage. While here, so now this is interesting. You are saying that threshold requires different surface potential. It requires a surface potential equal to so much here, and it requires a surface potential equal to so much here. These are two different surface potentials. At which threshold will occur? They're different. It's not the same thing here. All right, let's look at this let's continue with this one here. So we said at this point, surface potential at this point is at this one here. So again, we take this equation VGB, our usual equation here. VGB will be equal to V flat band plus 2 phi F. Instead of VSB, we'll write V drain to body. We write V drain to body minus Q inversion at the drain side by Cox. It's the same equation, but we are writing now at the drain end instead of at the source end here. So everywhere, instead of S, we have D here, and we have D here, and we have Q inversion at the drain side here. I can take this equation and rearrange it. Q inversion D equal to minus Cox. Now note VGB minus VDB will be equal to VGB minus VDB will be equal to VGD, which I can write as VGS minus VDS. Which I can write as VGS minus VDS. Okay, and so I have VGS minus VDS, and all these other terms I've collected here. So Q inversion is minus Cox VGS minus VDS here. I can take this and rewrite this big equation that you see here. I can write it as Q inversion on the drain side is minus Cox VGS minus VT minus VDS minus gamma plus this term. I can write it in terms of VT. VT was the definition of VT where? This VT at this VT here, at the source end here. At the source end, this is VT at the source end here. So when we define VT in a MOSFET, although we know VT will be different at different places, we define VT at the source end always. Okay, so it's always with respect to the source end here. So that's why I've written it out in terms of here. So we've written it out VGS minus VT, VT at the source end minus VDS minus gamma plus this term. So that's the inversion charge at the drain side here. At the source side, how much was it? Cox VGS minus VT. But at the drain side, it is this VDS also comes in picture plus all this term. So now, if you look at a MOSFET like this here, at the source side, as I said, it is VGS minus VT. At the drain side, it is VGS minus VT minus VDS and all this here. In general, as I go along the channel, how will it change? So voltage here is source, voltage here is drain. And as you go along the channel voltage will vary from Vs to Vd. And therefore, I'm generalizing it here and writing that inversion charge at any point, Q and X will be equal to minus Cox, VGS minus VT, same. Instead of drain, if I'm looking at any particular point in the channel, we're calling that voltage as channel voltage X, minus gamma square root 2 phi F VSB, same everything. Instead of VDS, we're writing the channel voltage measured with respect to the source, channel voltage minus square root 2 phi F. So that's a general expression for how inversion charge will change as you go along the channel here. Okay, minus Cox VGS minus VT minus V channel X minus gamma and so forth. All right, so this is the general expression. Many times in simple models, what we do is, this causes complication for us, square root term. So what we do is, we approximate it. And we say, well, this term is a square root here, minus square root of this. This is not too large. And we take it as 0. And we say, Q inversion at any point X is equal to minus Cox, VGS minus VT minus V channel at that particular point. So it's a simplified model here, where we are ignoring this term here. Okay, and we get inversion charge at any point in the channel here. At source, well, V channel at the source is equal to 0, because remember, V channel is being measured with respect to source. So at source, this term is 0, and you get Cox VGS minus VT. At the drain end, this term is equal to V drain, and therefore you get VGS minus VT minus VDS. Right, but please be aware that there's approximation sign here. Actual Q inversion has this extra term here, which is also changing here. Okay, so now this will form the basis of our model for the current. The current equation that you know, W by L mu Cox VGS minus VT square and all that, all those current equations now I'll derive from this particular model. But remember, I'm ignoring this. So the model that we'll derive is approximate in that particular sense here. Okay, because this is not being included here. Okay, and in this definition, then VT is equal to VT0 plus gamma, this particular term. VT0 is the constant here, and gamma is the body parameter, and VT is being defined as VT at the source here. So that's the model for a threshold voltage in a MOS structure, 4-terminal MOS structure, and this is the expression for inversion charge in my channel. This expression. This, as I said, now we can start with this particular expression and derive a expression for current. Okay. Any questions before we leave? The variation. So I guess what you are asking is this significant? It is significant. It does cause error. Okay. Now think about the following. Let's ask the following question here. Suppose I start with this model and I derive an expression for current. Right? I get a certain current. And I know this is more accurate. Okay? So let's write down ID1. I get an expression for ID or value for current using the simplified Q equal to minus Cox whatever. And I get ID1 through the more accurate model. Which one will be larger? Which current would be larger? What is the, so what I'm asking is, what is the consequence of our assumption? The fact that we have neglected this, what is the consequence of our assumption? Which current would be larger? ID is greater than ID1? Why? Because this is a negative factor, right? This is a negative factor, so I am overestimating charge. I'm overestimating charge, and therefore I'm overestimating current. So the current would be a few percentage points below the limit that we, this thing here. We calculate here. It's not that I cannot use this equation and derive an expression for current. One can do that also. This square root is not a very hard term. You know, when I try and derive an expression for current, square roots are easy to handle. Okay, so there are better expressions for current where the whole thing is taken into account and one does the derivation here. Okay. All right. So the next thing, how much time do we have? Okay, so in the remaining time, let me quickly go over MOSFETs that you are familiar with. And then in the last lecture on Monday, we'll derive the current equation. Okay, so stop me at any point of time. Symbols, all of you know, right? MOSFET symbols, right? Okay. Body contact, typically we make it at the top, right? So this is, you're familiar. P-type is here. P-type, typically, you know, we use a one single substrate and we create an N-well. These are all from E210. And so we make a body contact at the top. What it allows us is that, remember, the P-type is being made in a separate well. So each PMOS can have its own separate body contact and therefore a separate body to source voltage here. While in an N-type, all of them are being made on the same substrate. So source to body voltage is the same in all N-type here. Operation of the MOSFET. Well, now this is our inversion charge. We have said inversion charge will go like this here. Minus Cox VGS minus VTHN minus Vx here. So inversion charge is going to vary when you apply a voltage here. And, you know, inversion charge is, by the way, how thick do you think is the inversion layer? We've been saying there's an inversion layer, right? How thick is the inversion layer? What do you think is the inversion layer? Right? If you look at it, if you look at the energy diagram is going like this here. It's going like this, energy diagram. EF, EC is very close to EF, right? And electron density goes as Ns equal to Ni e to the power, you can write it as EF minus EI by KT, or you can write it as Nc e to the power minus EC minus EF. Sometimes in band diagram, this is better. So electron density is very high. Little bit in the bulk you go, what happens? Look at this EC. EC minus EF increases. What happens to electron density? Falls exponentially. So if I were to plot electron density, this is at the surface, this is X here, this is at the surface, how will it go? Exponentially drop. It just goes in. Right? And it will look almost like negligible, means on a linear plot it will look zero. So how thick is your inversion layer? How would you define inversion layer thickness? Maybe from the top to a point where it has fallen to half, roughly. So how thick do you think it is? How will you calculate inversion layer thickness? Well, if you look at this, ns is equal to ni e to the power ef minus er by kt. So how thick? Huh? Okay, yeah. How thick is this? Okay, huh? What is your guess? Huh? Pico, no, pico is very small. Nanometer, yeah.